So if you go to the website and you go to assignments, you'll find assignment 2 is problem set 4, okay? So you have about 10 or 12 questions. If you open this PDF file, some of them in chapter 8, half of them in chapter 8 and half of them in chapter 9, okay? The due date for this is next Wednesday, so one day before the quiz. So this will be a good exercise to prepare for the quiz, okay? Regarding the quiz, as I mentioned last time, you will have it online. Make sure that you you have a camera, as I mentioned, like a webcam. Just focus on your face. I will send you all the instructions shortly, but make sure that you have the webcam, you have some way to scan, your work. So it's going to be multiple choice and fill in the space. Just you like some numerical questions. You just write the numbers. But I need to see your work. Just to make sure that you don't lose any marks just because you mistakenly you choose the incorrect answer, or just you didn't write the correct answer in the blank. So make sure that you have a scanner at home, or you can scan with your phone using a nice software, and also organize your handwriting work. Don't make it messy. So make it clear so that I know that this belongs to this and this belongs to this. Okay. Any question about the quiz or the homework? Okay. As I mentioned before, we can do a third quiz if you like. To improve the marks for the quizzes. Okay. So we can think about it. Maybe we can do it after quiz 2. We can make another quiz, and we take the highest grades of the 3. Okay. So we average on the highest 2 out of the 3 quizzes. So, but we need to have this maybe outside the class time, because we don't have time to take off the class time. So maybe we choose another day, even in evening. Evening is fine for me. We can do it evening, no problem. Just let me know what's the best time and date. If you like. If you don't like, if you don't want any extra quizzes, that's fine too. Okay. So let's go back to the lecture that we started last time. I think we stopped somewhere. Here, I believe, right? We stopped here. Hello? Any answer? Did we stop here, or? It seems that I have to ask many questions to make sure that everybody's here. Hello? Is Kristen here? Jessica, are you here?
Yes, I am.
Okay. So why don't you answer? You know, I'm asking questions, nobody's answering. Matt, are you here? Miguel?
Yes, I just connected.
Okay. Okay, so yeah, I'm afraid that you just start, you know, the Zoom and just you leave. Okay, so my question, did we stop here in this slide last time? Do you remember?
I think we did.
Okay, yeah, I'm sure that we stopped here. Okay, so please, you know, participate in the lecture, you know, and ask questions or add comments. Feel free to ask any question at any time, so that I understand or I know that you are here. Okay. Anyway, so we were talking about the active filters using operational amplifiers and some other components, basically resistors and capacitors. And we talked about the first order stages, which has only one capacitor and can do only Butterworth approximation. And we talked about the design of them, and now we are talking about the second order stage. And we said the second order stage can have transfer function similar to this in general, which has something new compared to the first order, which is this peak here. Okay, and this peak depends on a parameter called Q. Okay, so Q is called the quality factor, or a parameter that determines this peak. And the higher the Q is, the higher this peak. Okay, and if Q is greater than 1, you will have this peak. Actually, you start having it after 0.707, the 1 over square root of 2. If Q is less than 0.707, then you don't have any peaks. You assume that the transfer function doesn't overshoot at all. There's no overshooting. But if you have Q that's higher than 0.707 or roughly higher than 1, then you'll start having this notch here, or this peak value at the frequency W peak. And this frequency, if you notice here, is not aligned exactly with omega 0. So it comes slightly before omega 0. And this happens due to a single pole that's very close to the imaginary axis. If you plot the poles and zeros of this filter, you will find the poles are very close to the imaginary axis. As they go closer to the imaginary axis, the high, you know, this height or this peak goes higher and higher. Okay. And we said this is the general transfer function for the second order filter. It has a numerator with these coefficients, A2, A1, and A0. Some of them might be 0, depending on the type of the filter, whether it's low pass filter, high pass filter, band pass filter, and so on. And in the denominator, you have coefficients here. This has to be 1 always. The coefficient of S square has to be 1. If it's not 1, you have to divide the whole equation by this number, or both the numerator and denominator by this number to make it 1. The S term is defined as omega 0 over Q. Omega 0 is the cutoff frequency, and the Q is the quality factor, as mentioned before, that determines the peak location or the pole location. And here you have omega 0 square, which is the cutoff frequency, the square of the cutoff frequency. The popular circuits that we can use to design something like this are one of these 4 types. The Salenki, the Friends, the two Thomas, the KHN, and these are the names of the people who invented or who proposed these circuits. And these are alternative names for the same circuit. So the Salenki is known also as voltage controlled voltage source filter. The Friends is also known as multiple feedback filter. The Two Thomas is also known as multiple op-amp biquads. It has biquads. And the KHN is known also as state variable filter. Okay. So if you see the different transfer functions for each type of filters, so for the low pass filter, A2 and A1 are zeros, and you only have A0, okay? And for the low pass filter, for the high pass filter, you have the S square coefficient, you don't have the other two coefficients. And for the band pass filter, you have the S coefficient. And for the band stop filter, you have the S square coefficient and the free term coefficient. And for the all pass filter, you have all coefficients similar to the same, exactly the same as the denominator, except with a negative sign here, which changes the phase response. So all what you need to know whether this is like if you are given a transfer function like this without knowing whether it is low pass filter, high pass filter, or band pass filter, or so on, you just substitute S with 0 and see the value. Okay, because when you substitute S with 0, that means omega is 0 because S is j omega. So when you substitute S as 0, then that means a very low frequency. So you find the extreme frequencies. Very low frequency means that omega is 0, which means S is 0. So if you put S as 0 here, then this term will be 0, and these two terms are 0. So this is going to be 0 divided by omega 0 square, which is 0. So this gives you a very low gain at low frequency. Now, if you substitute S with infinity, okay, to see the performance at high frequencies, this is gonna give you, if you substitute S with infinity, of course, it's gonna give you infinity over infinity, but you have to divide by S square to get rid of these high order terms. And this makes this 0 and this 0, this 0, and you end up with A2 over omega 0 squared. So at infinity or high frequency, the gain here is A2 over omega 0 squared, which is a constant, right? So you can understand now by just substituting at these extreme frequencies that this is a high pass filter. Why? Because at low frequencies, the gain is 0, and high frequencies, the gain is constant, which is A2 over omega 0 squared, and so on. You can apply this for all these transfer functions, okay? Now let's focus on the second order low pass filter. Why we focus on the low pass filter? Because using low pass filter, you can convert it to any of the other types. You can create any other type by just transformation. You do like you design the low pass filter. You just see the S plane and change the poles and zeros locations somehow. You convert this low pass filter. You can convert this low pass filter into a high pass filter. Okay, just change the capacitors and resistors. Maybe switch them. You move from a low pass filter to a high pass filter. So if you know how to design a low pass filter, most likely you will be able to design any other kind of filter. Like for example, a band pass filter is nothing but cascading. For example, a low pass filter with a high pass filter. Okay. With certain conditions, of course. Right? Okay, so knowing how to design low pass filter is very important to be able to design any kind of filters. Okay, so based on the this list here, this table, we can see that the low pass filter has a constant in the numerator, doesn't have any S, and this denominator. Okay, we will define this constant as H0 omega 0 squared. Okay, where H0 is the DC gain. Okay, why the DC gain? Because if you substitute S with 0, okay, which is the DC, because S, remember that S, remember that S equals J omega. Okay, so if omega is 0, which is the DC, that means S also is 0, right? So if you substitute S with 0 here, okay, to find H of 0, meaning S is 0 and also omega is 0, that gives you H0, okay? Because this term is gonna disappear, this term is gonna disappear, and you end up with H0 omega square divided by omega 0 square, and this cancels, so you end up with H0. So we call that H0, we call it the DC gain, okay, or static gain sometimes. So this is the DC gain. And in this case, you don't have any phase. The phase is 0 at DC, right? Because this function is going to be just pure real. There's no imaginary part. So it is. It doesn't have any phase. The only parameters that are unknown parameters of this equation or this transfer function are these three parameters, okay? And this is what we are just designing for. So designing the low pass filter, meaning that you need to find H0, omega 0, and Q. Because if you know them, you will know the transfer function. So the design problem will be given certain circuit, you know, a structure of a second order filter. And the question is to find, and we also give you these three parameters. And the question is to find the components that makes the transfer function with these parameters. The analysis problem on the other side, if I gave you the circuit, already built circuit with R's and C's, and the question is to find these three parameters. So you can do analysis for the circuit, or you can do design for the circuit. And we see two examples for design and analysis. Okay, now, so this is how to test the first extreme to make sure that this is a low pass filter. So at a very low frequency, when omega approaches 0, that means S approaches 0, and that means H of 0 equals H0. And when on the other extreme, before that extreme, let's substitute omega equals exactly omega 0. So we see what happened at this corner frequency omega 0. Well, you substitute omega with omega 0, and we know that S equals J omega. So S square, which is this term here. Okay, let me just delete this part here. Okay, so S square, which is J omega square, is going to be minus omega square. So this is minus omega square, and this is J omega 0. Okay, so this is going to be minus omega 0 square. Okay, and this is going to be J omega 0 square over Q. Okay, and this is omega 0 square. So omega 0 square will be cancelled with minus omega 0 square, and you end up with just this term here, J omega 0 square over Q. And in the top, you still have H0 omega 0 square. You cancel this with this, so you end up with minus J H0Q. Why minus J? Because 1 over J, if you remember, 1 over J equals negative J, okay? So this is the value of the transfer function, or the magnitude response at, actually the frequency response at omega equals omega naught. Okay, so we call that omega naught is the resonance frequency. Here we assume generally we have a Q that's higher than 1. So the circuit will make something called resonance. The resonance is the peak. Okay, so when you have a peak like this, okay, so the transfer function go up like this and then goes down. So this is called the resonance frequency. So omega, actually, as I mentioned before, the resonance frequency is slightly smaller than omega 0. It's not exactly the same. And the phase shift at omega 0, and in this case, is going to be minus 90 degrees. Why minus 90 degrees? Because we have minus J here. So minus J produces minus or negative 90 degrees. So this is a midpoint. So we tested the extreme point to the left, which is low frequency, and we tested the mid frequency, or the corner frequency, omega 0. Then we test the extreme, the other extreme, where omega is much larger than omega 0. Well, if you go up here and substitute omega with infinity, okay, so let's just delete this here. Okay, so if you substitute omega with infinity, what's going to happen? Well, that means this term, okay, this term will be much higher than the other terms, right? So this term is going to be canceled, this term is going to be canceled, and you end up with just this term here, right? So S square means, as we mentioned here before, it means minus omega square, right? Because S is j omega, so S square is minus omega square, and you end up with this value, okay? This value is almost zero, right? Why? Because omega is very, very large compared to omega zero. So this is approximately zero. But if you'd like to find the exact value, this is it, okay? And this is the reason why we say that the slope here is minus 20 dB per decade, okay? Why is that? If you take the 20 log of this value, so you're gonna get this equation, okay? Any questions? Okay. So this is the general transfer function or magnitude response of the second order filter. Here it's minus 40. I said minus 20. It's minus 40 dB per decade because it's the second order. If it's the first order, then it's minus 20 dB. Okay, and this will happen in the next in the previous one because you have square here. Okay, so if you take 20 log, this square will be sent outside the log, and you will have 40 dB per decade. Okay, so as I mentioned before, if you have Q less than 1 or 0.707 or less, then there is no peak. Okay, there is no height here, or there is no resonance. Okay. And this happens, at exactly Q exactly equal to 0.707. We call this, or this is if you have a Butterworth approximation. Okay, so in Butterworth approximation, Q is 0.707, and there is no resonant frequency. So if the question is asking to design a Butterworth approximation, directly assume that Q is 0.707. Okay. And of course there's no resonant peak. Okay, let's see how to find the transfer function. If you are given a circuit, how to find the transfer function of that circuit. Okay, well, I think you studied in electronics 1 the golden rules of analyzing the operational amplifier. The most important rules is that you assume V plus equals V minus. Okay, so these two terminals are virtually connected to each other. Okay, why is that? Because the gain of the amplifier is very high, and if the gain is very large, like infinity, then this makes V plus and V minus are the same. The second assumption is that I plus, okay, equals I minus equals 0. Okay, so there is no current IN. Okay, all the currents entering the operation amplifier from the inputs are 0. Okay, then you can use, if you'd like to quickly analyze the circuit, you can use these two well-known equations for the inverting amplifier and for the non-inverting amplifier. For the inverting amplifier, the gain is minus Z feedback over Z input. And for the gain, this is for the inverting amplifier. For the non-inverting amplifier, the gain is 1 plus Z feedback over ZI. I think these formulas are well known now. Okay, and we always typically do the sum of currents. The sum of currents means we do KCL. Okay, so we do KCL at input nodes. Okay, and in the input nodes to find out the transfer function. We never do KCL here. Don't do KCL here. We cannot do KCL here. Why? Because we don't know the current here. How to find the current here, we cannot tell, and we don't know whether we have a load or not. So basically, we don't do KCL at the output. We just do KCL at the input nodes. Okay. So let's move on. Okay, so let's start with the first circuit, which is the Sallen-Key circuit, the voltage-controlled voltage source. Sallen-Key filter is done this way. Okay, so you have 2 resistors and 2 capacitors. Okay, and in general, you have a Z1, Z2, Z3, and Z4. And you can play with these components. Just for example, like if you make these 2 resistors and these 2 are capacitors, this changes the design into a high-pass filter. Okay. Now, if you have these are resistors and these are capacitors, then it's a low-pass filter. So you can play with the location of the capacitors and resistors to change the performance from low-pass filter to high-pass filter to band-pass filter and so on. Okay. So like imagine like this. So you have a circuit like this. Okay. And the question would ask you, find the transfer function. And what type this filter is? Is it a low-pass filter, high-pass filter, band-pass filter, and so on? So all what you need is to follow the analysis similar to the one that we're going to do now. And at the end, you will have a transfer function similar to one of these transfer functions. Okay. So from the shape of the transfer function, you can tell whether you have actually from the numerator, okay? From the numerator, you can tell whether you have a low-pass filter, high-pass filter, band-pass filter, and so on. Okay, so this is the main point here. So let's analyze this circuit. Assume K here, the gain is the feedback circuit, you know, like it's not shown here, but this is it. You know, this gain K comes from a negative feedback, as you can see, from R, Y, and Rx. That makes the gain here as K. So we just abstract this here in this triangle and show it as K. But actually, in reality, this triangle here or this amplifier is this one. You have 2 terminals. The negative terminal has a feedback from the output with the 2 voltage divider resistors R1 and Rx. That makes the gain K. So just we simplify it by saying we have a gain of K here. Okay. Now we need to find H of S. The goal is to find H of S, the transfer function. As I mentioned, we said we have to do KCL at the nodes in the input. So we have 2 nodes here, node A and node B. We do KCL here and KCL here. Okay. I think you practiced this many times in circuits and electronics before. So at A, we have how many currents? We have 1 current here, 1 current here, and 1 current here. Okay. And remember that we like you have to use a convention whether you say that the current entering the node is positive or exiting the node is positive. So in this case, I assume that the currents entering the node is negative and current exiting the node are positive. Okay, so I will assume that I have 1 current going this way and 1 current going this way and 1 current going this way. Okay, so for this current, how much is this current? Well, this current is VA minus V input divided by R1, which is this one here. Okay, and how much is the current? This current here, this current is VA minus VB divided by R2, which is this one here. And the third current is VA minus V out. This is V out. Maybe it's missing here. So VA minus V out over the impedance here. Okay, so this is not a resistance. So the impedance here, Z equals 1 over J, not J, it's S. Let's use the S now. Okay. So this is SC1. Okay. So you divide VA minus V out divided by Z, which is 1 over SC1. 1, and this equals 0. Okay. Now we do the same thing for at node B. So at node B, how many currents you have? We have only 2 currents, right? Because the current here is 0. So the I here is 0. So there's no current this way. This is one of the rules we say that we say about the operation amplifier. So there's no current this way. Only you have 1 current here and 1 current here. So assume this current is going this way, and this current is going this way. Okay. So the KCL at node B is VB minus VA over R2, which is this current, and VB over R1 over SC2, which is this current, and this is equal to 0. You have 2 equations, but you have 3 unknowns here, or 4 unknowns. Like you have VA, VI, VB, and V out. We need to make this equation only a function of V input and V out, because the transfer function is V out over Vn. So we have to get rid of VA, and we have to get rid of VB. Okay. Well, we know that VB is the same as V plus, right? And V plus is the same as V minus. And V minus, if you go back here, this is V minus, right? V minus is the feedback portion of the output, okay? So it's V output times beta, if you remember from the feedback. So V minus is V output times Rx divided by Rx plus R1, okay? So if you go here, you will find this is 1 over K, right? Because K is 1 plus Ry over Rx. So 1 over K is Rx over. Okay, so this is why VB is V out over K. So we can substitute VB with V out over K and solve for VA here, okay? And then take this equation and substitute it here in equation 1. Then we will have this final equation. So if you just take this and substitute it here and rearrange the parameters and variables, then you will have this, and make sure that you always have S squared coefficient as 1. Okay, so you will have the function as this shape here. Okay, it's a bit nasty, but you know it's easy to, like, you can, if you substitute this and just go with the math, you can rearrange it this way. Once you do this, so this is H of S, okay? Now you compare this to the standard form. Okay, now you are not sure, is this a low pass filter or high pass filter or what, okay? So you look at the numerator, okay? What shape you have in the numerator, okay? The numerator here has just constants, right? There's no S parameter, okay? So this compares to the low pass filter, right? So this is a low pass filter, okay? It's obvious. Why? Because the numerator doesn't have any S parameter or variable. Then we can compare it to the standard form of a low pass filter, which is H0 omega 0 square divided by S square plus omega 0 over Q S plus omega 0 square. Always make sure that this part here is the same as this part. So we can see that omega 0 square is this part here. So this is the same here. So this is omega square, omega 0 square. It's not omega 0, it's omega 0 square. And this K is gonna be H0, right? Okay. And this part here, you know, the coefficient of S is going to be omega 0 over Q. So you equate these corresponding terms by each other, and you come up with an expression for omega 0, H0, and Q. So of course, omega 0 is going to be the square root of this part, because this is omega 0 square. H0 is K, as I mentioned here. And if you substitute this one here and this one, you're gonna come up with this one here. So Q is omega 0 divided by this one. So as you can see, like if it's a design problem, then you need to find how many parameters, how many unknowns of these parameters, R1, R2, C1, C2, and K. Okay, so these are the 5 parameters you need to define or to determine, given just 3 parameters, right? So I will give you 3 conditions. I will tell you like omega 0 is this, the gain is this, the quality factor is this. How much are R1, R2, C1, C2, and K? In this case, you have just 3 conditions, and you'd like to find 5 parameters or 5 unknowns. So you need more restrictions. You need more assumptions in this circuit. Like for example, C1 equals C2, R1 equals R1, R2, and so on. K is 1, K is 2. Like you have to give me like more restrictions to simplify this problem a little bit. Okay, so let's see some cases. So for case 1, if we assume K is unity, so we have a unity feedback. So this is a voltage follower. We don't have R1 and R2 like in the feedback, just to connect the output to the negative terminal. Then K is 1. Another condition or another constraint is R1 equals R2 equals R. So if we substitute in this case R1 equals R2 equals R, this is going to be R squared. You take it outside, so it's going to be 1 over R square root of 1 over C1, C2. Okay, so this is omega 0. And if you take omega 0 and substitute it here, omega 0, and also substituting R1, R2 with R, then you come up with this equation for the Q. Okay, so this is so the design problem simplifies to these 2 equations if you assume that K is 1 and R1, R2 are the same, which is R. But here, so now you just need to change 3 parameters, R, C1, and C2, okay, to come up with the 3 design quantities K, omega 0, and Q to satisfy these design parameters. But there's a problem here. Well, if you decide to have, for example, Q is 10, if you decide to have high Q a little bit, then if Q is larger than 10, for example, if Q is 10, then that means if Q is 10, that means C1 over C2 is 10 squared, okay, multiplied by 4. Okay, so it's 100 times 4, because if you take the square of these 2 sides, you will have C1 over C2 is greater than 400. You have to keep C1 over C2 greater than 400 to keep Q greater than 10. So for a reasonably large Q, you need to have the ratio between C1 and C2 more than 400. So that makes, usually these capacitors in the circuit are small capacitors in nanofarads, picofarads, and so on. Okay, mainly nanofarads. Okay, so if you have them this ratio, that means C2 will be much smaller than C1 400 times. So that means C2 might be a very, very small picofarad capacitor, which is susceptible now to strays, and we don't like to have a large ratio between the capacitors in the circuit. Okay, so it's better to have the values are close to each other. Okay, so this might make the circuit unstable, or like you will not find the exact frequency or quality factor in this case. Okay, but if you work with a low Q, like 1 or less than 1, this is a very good design and a very good set. So this is good for Butterworth for sure, because in Butterworth Q is 0.707. But if you'd like to make a high Q filter, in this case it's not going to be low pass filter anymore, because If you have a high Q, that means you have a notch, you have a resonant like this. So this is not a low pass filter anymore. So if you have a high Q, then this is not a good design. Okay. Other choice, if we choose K as 1, the same condition here, but we make the C1 equals C2. So we make C1 equals C2 equals C. Okay. So similar to R1 equals R2 equals R, we make C1 equals C2 equals C. In this case, this method is not going to work. Can someone tell me why? Like if we assume that the two resistors are the same and the two capacitors are also the same, so this circuit is not tunable. You know, it's not going to work. Can you tell me why is that? Try to check this equation here. Any answer? Okay, so basically, simply, you know, like if you choose C1 equals C2, that means this Q is just a half, right? So it's not tunable. You cannot change. Like if I ask you to design, can you design it with a Q of 10 or Q of 5? You know, no, you fix Q at half. So there is no way to redesign this circuit in another Q. Q is half and that's it. So it doesn't work because you already fixed Q at a certain value, which is half, no matter how much C1, C2 R is, okay? So you might be able to change the frequency a little bit, but Q is half. So actually Q is half means that the curve is going like this way, okay? So there's no resonance and it's not sharp enough because Q is less than 0.7. So there's no way to modify or to change Q because you already set Q as half. Okay. Any questions? Oh, a few number of students today. Okay. Okay. So the second case, we assume that K is 2. Okay, so we assume K is 2. And we assume that R1 C1 equals R2 C2. And if this is the case, that means omega 0 is 1 over R1 C1 or 1 over R2 C2. Okay. In this case, if you substitute omega 0 with these values, okay, in the formula here, in this formula, okay, that will give you, and I urge you to do this at home, you know, like all these derivations and these things, you try it yourself at home. So the Q will be C1 over C2 or R2 over R1. So this way, like by choosing K as 2, and it has to be exactly 2. Why is that? Because in this case, this term here will be 1 minus 2. So this term will cancel with this term, right? Because this is 1 minus 2 is minus 1, and this is plus 1. So this cancel with this, and you end up with omega 0 over 1 over R1 C1. So if you do this, you end up having these two equations, which is a versatile circuit capable for implementing any Q, right? Because Q now depends on R2 over R1 or C1 over C2, okay? Provided that you have this issue, you can maintain these values, okay? It's not easy because you are now, if you play with a C1 over C2 to change Q, this will change omega 0, okay? So this is the point here. If you try to adjust C1 and C2, R1 and R2 to make Q, then you will most likely lose omega 0. So you have to work very carefully with these values. And this is what we meant, you know, like two things. We need the circuit to be easily tunable. You can change the Q and change the omega 0 as much as you can, and change K as well. And at the same time, we make it less sensitive to the parameter change. Okay, if one parameter of one of these constants or one of these values of R1, R2, or C1, C2 changes, the change in, like, due to error or tolerance or any small change, this small change should not affect too much, you know, the omega 0 and Q. Okay, we're going to see an example now. So the third case, if we just assume K is generally greater than 1, but in this case, we assume that R1 equals R2 equals R, C1 equals C2 equals C, but under the condition that K is not 1, it's not 2, it's greater than 1, okay, in general, whether it's 2, 3, 4. So in this case, case 2 is a subcase of case 3. So if you choose this 3 condition, if you do these 2 constraints or assumptions, then omega 0 is going to be 1 over RC, and Q is going to be 1 over 3 minus K. Okay, well, this looks very nice. Why? Because to tune K is not tuning Q by just changing K, okay, is not going to affect omega 0. So omega 0 depends completely on R and C, but Q doesn't, okay, which is good, you know, from the tuning, the easiness of tuning point of view, this is excellent. Why? Because you can just tune up Q by changing K. And while you're doing this, you are not affecting omega 0 like in the previous one, because here if you tune Q, you have to choose C1 and C2 and R1, R2 or R1. And if you do this, you're gonna affect omega 0. But in this case, they are independent, right? But there's another drawback here. What's that? If you calculate the sensitivity of Q with respect to K, like if you have, like let's take this example here. If Q is 10, to design Q as 10, then you have to select K as 2.9. And what's K? K is defined by, if you go back here, K is defined by this beta or feedback resistors here. You know, K is defined by Ry and Rx, right? So if you need a Q of 10, then you have to design Rx and Ry to give you a K of 2.9, right? If anything happened to Rx and Ry, like for example, you change them with another resistor with a slightly different value or a certain error or a temperature problem or something like this, and K changed from 2.9 to 2.95, so this is just a 1.7% of change, then Q will change by 100%. So Q will change from, and try it, you know, try to plug in your calculator now, 1 over 3 minus 2.9, this is going to be almost 10, and 1 over 3 minus 2.95, this is going to give you 20. So just a small change, okay? Remember the sensitivity? We said the sensitivity of Q with respect to K is delta Q percentage over delta K percentage. So the the error or the difference, the change in Q relative to the change in K. Okay, so this is a very large number because the change in K in Q now is 10, while the change in K is just 0.05. So this is going to be 10 over 0.05. So it's a huge sensitivity. So this system is very sensitive on the variation of K. So the calculation of Q is very sensitive on the change in K. While it is good in tuning, like because you can tune K independently of omega 0, but the Q is very sensitive on the value of K. Any questions here? Okay. Now we'll take two examples. The first one is an analysis example, and the second one is a design example. Okay. So analysis, I am giving you the circuit with the components, and I'm asking you to find the three parameters H0, omega 0, and Q. Okay. We can see that K is 1 because this is a unity feedback. You don't have any resistors for the feedback, so K is 1. And you know that H0 is the same as K, so H0 is also 1. Okay. Now you have R equals R, so this is case 1. If you go back here, when you make R1 equals R2 equals R, and K is 1, so this is case 1. Case 1 has K is 1. Okay, case 2, K is 2. Case 3, K is greater than 1. Okay, so this is not case 1, case 2, or case 3. This is case 1. So in case 1, we know that omega 0 is 1 over R square root of C1, C2. And if you plug in the values of R and C1, C2, you will get this value. So omega 0 is 28, almost 29 kilo radian per second. And Q is half, if you remember case 1, half C1 over square root of C1 over C2, which is 1 over square root of 2, and which is exactly 0.707, which means that this circuit is a Butterworth filter, because we said when Q is 0.707, this is the Butterworth filter case. So this is a Butterworth filter. Now we have H0, omega 0, and Q. Let's plug them in the standard equation of a low-pass filter. Okay, that gives us this equation here. So if you plug in these values in this equation here, you get this value. Okay. To make sure that this is a low-pass filter and to see the performance according to these parameters, I used MATLAB to plot it. And if you'd like to plot a transfer function, magnitude response, actually we are plotting a frequency response, not the transfer function. It's a h of omega what we plot. So to do this in MATLAB, you define the transfer function and you put here the coefficients. So these are two vectors. The first vector is the numerator coefficient, and the second vector is the denominator coefficient. If you go back here, you see the numerator coefficient, we have only one coefficient of 8.26 times 10 to the power 8, which is omega 0 square. And in the denominator coefficients, we have 3 of them. This one is 1, has to be 1 always. And this one is 4.07 times 10 to the power 4. And this one is 8.26 times 10 to the power 8. If we substitute these values, these are the only coefficients of the denominator. And this is 1, 4.7, 4.07, 10 to the power 4, and 8.26 times 10 to the power 8. And you use the command body. So body will plot the magnitude response and the phase response. Okay. And as you can see here, many things. First of all, that this is a Butterworth. It's maximally flat, right? This is flat all the pass band. Of course, it's not 100% flat from low frequency to omega 0. If you zoom in, you will find, slowly, slow slope here, okay? But, in general, if you look at the general magnitude response, you'll feel that this is almost flat. And at this frequency, if you go here, and you find the cutoff frequency, this should be the omega 0. Okay, so this is omega 0 that we calculated in the previous page. Okay, and this slope here is, as we said, minus 40 dB per decade, because this is a second order. Okay, so this gives, and you can see that also the phase is non-linear phase. Okay, if it's a linear phase, it would have been like this. You know, okay, if it's linear phase, then it would have been like something like this. Okay, a straight line. Okay, but now this is a non-linear phase. Okay, the non-linearity is not too much. If you increase Q, if you have a peak here, the non-linearity will be much higher, will be something like this. Okay, so the non-linearity increases if you have fluctuation here in the passband. Okay. Next question is a design question. I'm giving you a circuit. I would like to design this circuit, meaning that I need to find R1, R2, C1, and C2, provided some constraints or assumptions. The first assumption, or the first design parameter, is that I need omega 0, or actually F0 in this case, to be 20 kilohertz. You know, the cutoff frequency, the bandwidth of my filter, and this is the bandwidth. Bandwidth is the same as the cutoff frequency, right, for the low-pass filter. So the bandwidth is 20 kilohertz, and I need to have C2 as 56 picofarads. Assume this is the only value I have in the lab, for example, or something. And I need to make R equal R1 equals R2 equals R. Okay, so provided these conditions, plus also the gain is 1. You know, I don't need any gain. I need the maximum gain to be 1. So provided these 3-4 conditions, first condition, first assumption that the bandwidth of the omega 0 is 2 pi times 20 kilohertz. Second is that C2 is 56 picofarads. Third, that H0 equals K equals 1. You have a unity feedback. And the fourth one is that R1 equals R2. Well, using the same design, because since this is case 1 as well, because K is 1, and Q, and I'm saying here this is Butterworth. Okay, this is also another restriction. I'm saying this is a low-pass filter, Butterworth, and I said here 2-pole low-pass filter. What does 2-pole mean? When I say 2-pole low-pass filter, what does it mean? Sorry?
It has 2 poles.
Yeah, what does it mean? What's the implication of 2 poles? When a filter has 2 poles, what does it mean? It's a second order filter, right? So the order of the filter is determined by the number of poles, and the number of poles is determined by the number of capacitors. If you have 2 capacitors, that means you have 2 poles, and that means you have a second order system. Okay, so the word 2-pole here means second order system. Okay, 3 poles, third order system, and so on. Because normally the denominator here has higher order or equal order like the numerator, right? So if you have 2 poles, you will not have more than second order, right? So this is second order system. If you have 3 poles, that means you have a third order system. So the number of poles determine the number of the order of the system. Okay, so based on this information, I can start the design process. Okay, first thing is that since this is a Butterworth, then Q is 0.707, and since this is case 1, where K is 1, then Q is half square root of C1 over C2. Okay, so substituting C2 with 56 picofarad, which is 56 times 10 to the power minus 12. And this is C1. We can solve for C1 here and find C1 as 112 picofarad. You see, the 2 capacitors are like comparable to each other. You know, the values are close. You know, they are not like one of them picofarad and the other one microfarads, for example. No, they are almost in the same range. Okay, this is double this one. Okay, Now, from the omega 0 equation, we know that omega 0 is 1 over r square root of C1, C2. And r is unknown, C1 and C2 are known, and omega 0 is also known to be 2 pi times 20k. Then we solve for r to find it as 100.5 kiloohms. The only problem here is that C2 is standard, 56 picofarad. If you remember in the lab, you can find this value in the lab because you cannot find physically, like in the market, all the values of capacitors that you need. You know, you have to go with some standard numbers. So 56 picofarad is a standard number, but 112 is not a standard number. You will not find any unless you, if you remember, we put 2 in parallel or 2 in series or whatever. You can combine some series parallel connections to make this. But if you'd like to use one single capacitor, the closest standard one is the 120. So you will find 120 picofarad. And also 100.5 kilo ohm resistor is not a standard one. The closest one is 100K. So if we use 100K instead of 100.5, if you use 120 instead of 112, this will give us 20.1 kilohertz bandwidth instead of 20 kilohertz, which is not a big deal, you know, like just 0.1 extra, but you know, it's reasonable. Okay. So this is how to design a second order low pass filter using these conditions. Okay. Yes.
Was Q given?
Q?
Yeah, was it given in that part?
Yes, it's given in this word here. When I say Butterworth, right away you assume that Q is 0.707, okay, which is 1 over square root of 2. Okay, this is given. So whenever you see Butterworth design, so that means I don't need any peaks, any resonant peak. So that means Q is 0.707. So this is why I substituted Q with 0.707. If it's not mentioned that it's Butterworth and Q is given, you just use that Q. Like I can say Q is 2, Q is 5. So you use that Q. In this case, you will have a peak. You know, you will have something like this, and then it goes down. Okay, you will not have a nice one like this one here. Okay, instead you will have, if Q is bigger than 1, this will go flat and then go up and then go down. Okay. I also encourage you to do that, like at home. If you just take this code, okay, and maybe go to whatever example. Maybe you can take this example here, the first one, okay. Oh, actually, let's go to the second one. Take this one and make Q as 2, for example. Okay, and from this calculate C and R and everything, and find the transfer function. Okay, so the transfer function will be H0, which is 1, times omega square, which is this value square, divided by S square plus omega 0, which is this value, divided by Q, which is this value, times S plus omega 0 square, which is this value square, and put it in a form like this. Okay, substitute the values and put it in a form like this. Okay. Okay, let me show it to you. Okay, so I think I have the code for this one. With Q is 0.707. Where is Q here? Q is in this term, right? This is omega 0 over Q. So if you reduce this value here, we are increasing Q. So let's reduce this value by a factor of 4, for example. Okay. So let's make it 1.0. Instead of 4, we make it 1. Okay. So let me go here. I think I have to exit first. Yeah. Okay. And this is yeah, this is the function here, H. Okay, let me change. Can you see the MATLAB desktop?
Yes.
Okay, so let me just, first of all, I will run this. Okay, this is H, okay, and I will write body, okay, body of H, okay, and this is what you see as the output. System is a bit slow. Yeah, this is the output. You can see this is a nice Butterworth filter, no peaks, nothing, okay? Now, if I change, oops, if I change in the H, in the transfer function, this to, let's say 1, okay? So I reduce this, meaning that I increased Q, right? Q now is almost 4 times, okay? So now if you do body plot, you can see the notch here. You got it? Okay. And you now can see that the nonlinearity in the phase is higher, right? Okay, let me go back. Okay. Oops. So this is the original one. What's this? Okay, please no one try to use the annotation tool, okay? So this is H. This is body plot, okay? And this is the new H. And I will open a new figure, okay? And I will plot it in the new figure. So now we have 2 figures, this one and this one, okay? So now you can see, come on. Can you see the both of them? This one is a Butterworth with Q equals 0.707. So it's maximally flat, no peaks, no ripples, no jumping up and down, nothing, it's flat. And then it goes minus 40 dB per decade. And this is the phase. Phase is almost linear. It's not 100% linear, but it's almost linear, okay? Now, if you increase Q a little bit, you will have this peak here, okay? And the phase becomes more nonlinear. Okay. Now let me just maybe increase Q more. Like in this case, Q is 0.707. The second case, Q is 4 times the value of this Q. Okay. Now let's do this, for example. Let's make this 0 point something. Okay. Let's make it 0.1. Okay. Just 2. Okay, and then I will do a body plot again on the right figure. So this is the first one. This is the second one. See now the peak value or the notch or the resonance becomes more sound more higher, and the nonlinearity becomes more. Okay, because if it is linear, you should have a straight line like this. Okay, but now it's non-linear. This one is closer to the linear, right? Sorry, I didn't draw it well. Okay, so this is, if it is linear, it's gonna be like this. Okay, so you can see that the non-linearity here is higher than this one. So of course this is not gonna be a low-pass filter. If you design a filter like this, this is not a low-pass filter. Why? Because the gain here is much higher than the gain here or the gain here. But this is a low-pass filter. This is a nice low-pass filter. You design this one here to have a band-pass filter, actually, a notch, like a narrow band-pass filter. A low-pass filter with high Q gives you a narrow band-pass filter. Okay. Any questions? Okay, that's it. We're gonna continue repeating this in all other circuits. Okay, so let's go to the next circuit, which is the friends. Okay, friends here is called multiple feedback filter. So instead of having the feedback of the non-inverting part for K, we utilize this as a capacitor feedback with the original feedback. So so we have two feedbacks here. This is why it's called multiple feedback. One feedback with a capacitor for the filtering part, not for the gain. Okay, so we do the same thing. You know, if you'd like to find H of S, you have to do KCL at node A, at node B, and find H of S. If you do it at node A, you have how many currents? You have 4 currents. Okay, one current here, one current here, one current here, and one current here. Okay, and you assume this one is ground, right? This one is ground. Why ground? Because these V minus and V plus are the same. And since V plus is ground, then V minus is also ground. So to find the current, this one here, VA minus VI divided by R, which is this term here. This current here, this current is VA minus 0, because this is 0, divided by 1 over SC, which is this term here. And the current, this current here in this side, between VA and VB, so it's VA minus VB divided by R3, but since VB is 0, then VA divided by R3, which is this term here. The last current, or the final current, is between VA and V out, so it's VA minus V out divided by R4, and this equals 0. Done. We are done with the first equation. The second equation is KCL around node B. So you do around node B, so VB minus VA over R3, which is this one. And since VB is 0, this will delete VB, so you end up with VA over R3. Plus the other current, which is this one here, it's VB minus V out over 1 over SC, which is this term here. This equals 0. Okay, and remember that V differential, which means V plus minus V minus is 0, and the current, input current is 0. Okay, if you rearrange this equation, you'll get this equation. Substitute in the first equation, you will, and keep arranging and rearranging the parameters until you reach this transfer function here. Okay, so this transfer function is put in this way to keep this coefficient here as 1, coefficient of S squared is 1, and the coefficient of S is omega 0, don't forget this, over Q. Okay, and this coefficient here, the free term, is omega 0 squared. And this term here, this free term here on the numerator is constant, which is K, this is K or H0 times omega 0 squared. From this, you can find omega 0, which is the square root of this part, H0, which is K, which is this part here, and Q is this omega 0, this term divided by omega 0. Okay, like how to find Q from this term and this term. So you substitute omega 0 with this value here, and you get Q. Okay, so as you can see, it's more complicated, but it's a versatile design. You can design it for any omega 0, any Q without any problem. Sensitivity is not high, but the problem is that omega 0 and Q is difficult to tune. Why? Because if you tune omega 0, you have to select R3, R4, C2, C5. Once you select them, you will determine Q. But if you have a different Q, then changing these values will affect both of them. So Q and omega naught are dependent on the same parameters or same constants. Okay, so changing these values will change omega naught and Q. So it's difficult to adjust or tune. Okay. The third one is tautomous, which is called biquadratic. This one is more versatile and easy to tune. Okay, but the problem is that it's more complex. Okay, you need to add a third operation amplifier. So you have 3 operation amplifiers instead of having 2. Okay, but it's much easier to tune just independently. You are just Q and omega 0 independent. Okay, again, we are going to find the H of S and find H0, Q, and omega naught. Okay, how to do this? You do KCL here, KCL here. You have these equations. You rearrange them until you find the H of S like this. So if H of S is like this, you equate it with the standard equation, and you find omega 0, which is going to be 1 over RC. H0 is R over RG, and Q is RG or RQ over R. Here we made an assumption, I believe, that, yes, we made these two assumptions, that R1 equals R2 equals R, and C1 equals C2 equals C. Okay, to simplify the life a little bit. So if you do this assumption, you're going to end up with these parameters. Okay, now can you see that it's easy to tune? Yes. Why? Because Q is tunable using just R. You know, the common value between Q and omega 0 is R. So if you fix R here and here, then you can play with C and RQ to change for certain Q and for certain omega 0. So that makes it easier to tune. Okay. The fourth one is the KHN. This circuit is called also the state variable filter. I didn't show you here the how to find the transfer function, but I leave this as a homework. So this will be the assignment 4 or 3 actually, so assignment 3. So is it easy to find the H of S for this one? Can you do it like based on what we have done here? So I need you to follow the same steps as we did for the previous 3 types, okay? And try to find H of S here, okay? So and I'll keep this as assignment 3, okay? Find H of S. And from this H of S, you need to find Q, omega 0, and H0. Okay, so all what you need is to take KCL here, you take KCL here, and KCL here. Okay, with these 2 intermediate outputs, you have one. The good thing about this one and the previous one, it's not only give you a low pass filter. This one actually gives you the 3 filters at the same time. So if you take the output from this side, you will have a high pass filter. If you take it from this terminal, you have a band pass filter. If you take it from this one, you have a low pass filter. Okay, so basically you have a low pass filter like this. Okay, let me change the color, and you have a high pass filter like this. And if you change the color, and you have a band pass filter like this. Sorry, you know what this is. Okay, so you can have the 3 filters with this simple design, with one design. Okay, the only disadvantage here is the complexity of the filter. You have 3 op-amps instead of 2, but you still have 2 capacitors. So this is a 2-pole second order filter. It's not third order. Okay, we don't calculate the op-amps, we calculate the number of capacitors in the circuit. You have many resistors, 3 op-amps, but you have 2 capacitors. This is a second order. Okay, so from the circuit, you can determine directly whether it's a second order, first order, third order based on the number of capacitors. Second, you find H of S, and from the form of H of S, you can determine whether it is low pass filter, high pass filter, band pass filter, and so on. And you can find Q, omega 0, and H. Okay. This is a comparison between the 4 of them. These are the alternative names. This is the complexity. The lowest complexity is the Sallen-Key, and the highest complexity is these 2. Sensitivity. This have high sensitivity, as we saw on the parameters. These 2 have very low sensitivity. This is easy. The last 2 are easy to tune, but the first 2 are difficult to tune, and these are the advantages of each one. Okay. Also, approximations that you can make out of these ones. If you'd like to have a Butterworth, which is maximally flat, and monotonic in the stop band, you can use these, any one of the four. If you'd like to make a Chebyshev, which has these two features, then you can use any one of the four. If you'd like to have inverse Chebyshev, which is type 2, you can only use KHN. Elliptic also KHN, the Bessel you can use any one of the four. Okay, so this summarizes the different types of filters that you can design. Okay, so that's it for the active filters. I know that there are other parts in this filter, but you can study them later on. But you know, these are the most important steps on designing a second order and first order. Why? Because you can create any higher order by combining first and second order. Any questions? Okay, thank you. Yes.
Is lab due today?
I forgot, to be honest. Did we?
Lab 3?
Lab 3. Yes, I believe.
Okay. I'll just check.
You might, yeah, check the website, you know, the Canvas. I have the deadlines in Canvas. Okay. Okay, thank you so much. Wish you all the best, and please be prepared for the quiz too, and follow the instructions that I will send you regarding on the preparation and things you have to have at home before we start the quiz. So that would be good practice for the final exam. Okay, and let me know if you all agree with having a quiz 3 or not. Okay, thank you so much. See you next time. Goodbye.